Okay, so today we're going to go over section 9.6 and we're going to be talking about the ratio and the root test. So we've already talked about a geometric series, and you'll recognize a geometric series by the way its formula is written. You'll have your index will be in the exponent and your base will be constant. And so then this is what it'll look like. And the base is called the common ratio, and if the absolute value of the common ratio is less than 1, then your series will converge, and we also even have a formula for what it will converge to. If your absolute value of the common ratio is more than or equal to 1, then the series diverges, right? So that's all well and good. Now again, one way to determine if a series is arithmetic is by taking the ratio of the a sub k plus 1 and dividing it by the term before it. Take any term, divided by the term before it. If this is always the same number, then it's geometric. And so this ratio here of the term divided by the term before it is the motivation, or what sparked the idea for the next test. The next test is called the ratio test, and it says let the summation of a sub n be a series with non-zero terms. The series a sub n converges absolutely, and therefore converges, if the limit as n goes off to infinity of the a sub n divided by the a sub n plus 1 divided by the a sub n is less than 1. So let's see why this is working, right? So suppose we know that the limit as n goes off to infinity of the absolute value of the a sub n plus 1 divided by the a sub n is equal to r, and r is less than 1, right? Now since now what this really means, we haven't spent too much time on this, but what this really means is that as you go further and further to the right, you get closer and closer to r. That's what it means for the limit to be r. That's what we've been saying most of the times. But another consequence of that is you can pick as close as you want to get, and then there will be index, an input, so that if you are beyond that input, you are as close or closer than how you chose to, how close you got to choose. How close you chose to be. So then another way of saying that is if the limit as n goes off to infinity of a sub n plus 1 over a sub n is r, then you can pick any number between r and 1, and then there has to be an n such that the absolute value of a sub n plus 1 divided by a sub n will be less than r, because you can get as close as you want to, so then you can always find an n so that this and this is going to be less than 1, and for n bigger than some n, right? So bigger than or equal to, right? So that's a consequence of you getting closer and closer to little r, means that you can get as close as you want to little r, and that means then that after some n value, all your terms will be closer to little r than this big R, right? So they just keep getting closer and closer, so eventually they'll move away from this. And so then what that implies is that for this particular n, the a sub n plus 1 divided by the a sub n, the absolute value, is less than r. And if we multiply both sides of this inequality by the absolute value of a sub n, we get that the absolute value of a sub n plus 1 is less than the absolute value of a sub n times r. Okay, sorry, and this should be a capital N. Okay, and now, so then this works for all of them. So if we substitute in n plus 1 for n, then the absolute value of a sub n plus 2 will be less than the absolute value of a sub n plus 1 times r. Okay, but if you come over here and multiply both sides of this inequality by r, you get, I'm sorry, if you come over here and multiply both sides of this inequality by r, you will get that r times the absolute value of n plus 1 is less than a sub n times r. And so then, so this is less than a sub n times r, and you already have an r there, so you get a sub n times r squared. Right? And now if you do the same thing for a sub n, if you substitute in n plus 2 for n right here, then you get the absolute value of a sub n plus 3 is less than the absolute value of the term before it, which is a sub n plus 2 times r. And if you go to this inequality right here, this should be a capital N. And this should be a capital N. And if you go to this inequality, if you go to this inequality right here and multiply both sides by r, you realize that, I'm sorry, if you go to this inequality right here and multiply both sides of this inequality by r, then you will get that the absolute value of a sub n plus 2 times r is less than the absolute value of a sub n times r cubed. And you can continue this, and then what you have on the left is a series whose terms are less than the terms of this geometric series over here on the left, on the right. Right? And so on the left you have the terms of a series that are less than the terms of a geometric series. Since the geometric series converges because your r value is less than 1, then your r value here is less than 1, then the whole series converges and the original series converges. Right? So that's the argument there. Likewise, if you look at the limit of the ratios, and if your ratio is bigger than 1, then that pretty much tells you that eventually your series is increasing. And if your series is increasing, then your terms can't go to 0. And if your terms can't go to 0, then your series has to diverge, which is what number 2 was telling you. And now for number 3, it says the ratio test is inconclusive, or when the limit as n goes off to infinity of a sub n plus 1 over a sub n is equal to 1. And the reason why it's inconclusive there is because if you use the ratio test on 1 over n, you will get that your limit is 1 and the series diverges. If you use the ratio test on 1 over n squared, this is a p-series with p being bigger than 1. This converges, but when you use the ratio test on it, you get your limit is 1. And so you have instances where the limit is 1 and the series diverges, and you have instances where the series is 1 and the series converges. So the test is inconclusive. So let's practice the test now. Okay. Use the ratio test for absolute convergence to determine whether the series converges or diverges. If the test is inconclusive, say so. So again, we have both positive and negative terms. So we're supposed to look at the limit as n goes off to infinity of the absolute value of the a sub k plus 1 divided by the a sub k. This then gets me my positive terms, and if this limit is bigger than 1, the series diverges. If this limit is less than 1, the series converges. If it's equal to 1, it's inconclusive. So notice that we have this factor here, and all this does is changes my terms to go from positive to negative, positive to negative. And so then when we absolute value, all that does is gets rid of this term. And so then the absolute value of the a sub k is just going to be 2 to the k divided by k factorial. Okay, so then the absolute value of a sub k plus 1 is just to go and substitute in k plus 1 everywhere you see a k. So you're going to substitute a k plus 1 there and a k plus 1 there. So you will get 2 to the k plus 1 divided by k plus 1 factorial. Okay, so then when we go and take the limit, right here, when we go and take the limit, we're going to divide the a sub k plus 1 by the a sub k. No need for absolute values because we've already got them right here. And so then what you are going to get is 2 to the k plus 1 divided by k plus 1 factorial. And rather than dividing by the a sub k, we'll multiply by the reciprocal. So we will get k factorial over 2 to the k. And, oh, I'm sorry. We're still taking the limit. We haven't taken the limit yet. Got to squeeze the limit in there. It's the limit as k goes off to infinity. My index that I'm using here is k, not n. Okay, and so then this becomes, we still haven't taken the limit, and we're still taking k to infinity, and we're going to do some simplifying, right? So with this one and this one, we can use the rules of exponents, and the rules of exponents say you subtract the exponents when they have the same base. Your base is 2, your base is 2. The exponents are k plus 1 and k. K plus 1 minus k is 1, and so you just get a factor of 2. With the k factorials, what we do is we break off a factor of k plus 1 in the denominator, and then times k factorial. And in the numerator, we keep it k factorial. And so then the k factorials go away. And then what we have is the limit as k goes off to infinity of 2 over k plus 1. Now the denominator is getting bigger and bigger without bound, and the numerator staying fixed at 2. So then this limit is 0. And so then the ratio test tells us that this converges, therefore converges by ratio test. So let's move on to the next one. Now what I strongly encourage you to do is I encourage you to try this problem on your own. Pause the video. Very difficult to listen to this for an hour. Instead, pause the video, try the problem, and then come back and see what you did, see what I did, and then you can see if you're getting this or not. Okay, so then again, the absolute value of the a sub k, we'll just get rid of this factor right here, and then we will have k over 5 to the k. The absolute value of a sub k plus 1 is then to just go to your formula right here and substitute in k plus 1 for k. So you end up with k plus 1 over 5 to the k plus 1. Okay, and so then we want to take the limit as k goes off to infinity of the absolute value of a sub k plus 1 divided by a sub k. And again, this is the limit as k goes off to infinity of the a sub k plus 1 is this fraction k plus 1 over 5 to the k plus 1 times the reciprocal of the a sub k. So to divide, we just multiply by the reciprocal. And so we get 5 to the k over k plus 1. I'm sorry, over k, no plus 1. Okay, so again with this one and this one, we can use the rules of exponents. And we can realize that we have k factors of 5 in the numerator, k plus 1 in the denominator. All but 1 will cancel out, so we'll end up with a 5, right? We could subtract the exponents. K minus k plus 1 will give us a minus 1, and then we have a factor of 5 on the bottom, whatever you like. And then there's no simplifying to do with this because of this plus, so we just end up with a k plus 1 on top and a k on the bottom. Notice that what we get here then is we have a rational expression where the degrees are the same, degree 1, and so we get the leading coefficient of the top, 1, over the leading coefficient of the bottom, 5. This is less than 1, therefore converges. By ratio test. And we move on. Use the ratio test for absolute convergence to determine whether the series converges or diverges. If the test is inconclusive, say so. Okay, so again, try the problem on your own. See if you can get it without any help, and then watch the video and make sure that you're doing things correctly. You might get the right answer, but if you're showing the wrong work, then you know that's not good. Okay, so we're going to take the limit as k goes off to infinity of the absolute value is just going to get rid of this factor right here. And so then a sub k plus 1, we're just going to replace the k everywhere we see a k, we're going to replace it with k plus 1. So we get k plus 1 to the k plus 1 divided by k plus 1 factorial times, okay, then we multiply by the reciprocal of the a sub k, so the reciprocal is going to put the factorial in the numerator and the k to the k in the denominator. This is then going to equal the limit as k goes off to infinity. So with the k plus 1 factorial and the k factorial, the bigger factorial is this one. K plus 1 factorial means k plus 1 times k minus 1. But the way we simplify those is by stopping once we get to the smaller factorial. So again, I did that kind of quickly last time because we've done this in class before. But what this is k plus 1 times k minus 1 times k minus 2 times, and we don't do that. We just write k factorial because there's a k factorial over here that we can cancel out. Okay, and then over here we still have the k to the k. And there should be a plus 1. I'm sorry, this computer wants to keep filling stuff in when it doesn't, when I don't need it to. So this becomes the limit as k goes off to infinity of, okay, and so then right here in this fraction right here, you can see that you have a base of k plus 1 and a base of k plus 1, that this exponent is k plus 1 and this exponent is 1, so we can subtract the exponents. So we can take the k plus 1 and subtract the 1. That will then leave me with a k plus 1 to the k. And then over here, we end up with just a k to the k. Okay, now then since these are both the same, right, it's not entirely obvious what this is, but since these are both the same, we can use the rules of exponents and rewrite this as the limit as k goes off to infinity of k plus 1 over k raised to the k. And then this becomes the limit as k goes off to infinity of, if we clean this up, we can break this up as two fractions, 1 plus 1 over k raised to the k. And if you're comfortable with what this limit is, you can write it down, but if you don't remember, then we've got this problem and that my variable is up in the exponent, right? And again, we've done this before. If I had a natural log here, then I could bring that down, and then but I can't just bring this natural log in unless I also undo it by exponentiating over here. And we can bring the limit inside, so we can do this, right? What this allows me to do is it allows me to take this exponent and bring it down here. And then so that we can L'Hopital this thing, we can rewrite this as the limit e to the limit as k goes off to infinity of the natural log of 1 plus 1 over k all divided by 1 over k. Right, so we don't just bring that k down here and leave it in front, because then we have infinity times 0, so that we can natural log it, so that we can L'Hopital it, we bring it down here. And now this is equal to, by L'Hopital, e to the limit as k goes off to infinity of the derivative of the natural log is 1 over the inside 1 plus 1 over k times the derivative of the inside. I've just caught something that I'm doing, but I'm running out of space and I don't want to go back and fix this. What I'm doing is I'm working with a series which we can't differentiate. With a sequence which we can't differentiate. But what I expect to see on your paper is you changing it to an x instead of a k. But the work is exactly the same. Notice I didn't take the derivative because I'm running out of space. ddk of the denominator, 1 over k. And so then what's going to go on is this will cancel out with this. And so then here you are going to now you can take your limit, and as k goes off to infinity, this right here goes to 0. And so then you get 1 plus 0, which is 1, 1 over 1 is 1, and so then this limit is 1, and so you get a limit of e. Now, had you just remembered that from first semester calculus, that's fine. But on your test, on your final, if you don't remember this, this is how you can go about it. But notice that this is bigger than 1, and therefore your series diverges. We move on to our second theorem of this section. It's called the root test. The series a sub n converges absolutely, and therefore converges, when the limit as n goes off to infinity of the nth root of a sub n is less than 1. Okay, so again, we're not going to go through the formal proof of this, but let's get an idea of what's going on. Suppose that the limit as n goes off to infinity of the nth root of the a sub n is equal to r, which is less than 1. Then eventually the nth root of a sub n will be less than some r value between this r value and 1. And if we raise both sides to the nth power, because that is an increasing function, then eventually the a sub n will be less than, oh, I'm sorry, I need absolute values in here. Then the absolute value of a sub n will be less than r to the n. And so then your terms are smaller than a geometric series that converges, and so then your series should converge. So that's why this is working out. Likewise, if your a limit is bigger than 1, then eventually your terms, the nth root of your terms is bigger than some number that's bigger than 1, and so then your terms don't go to 0, so your series is going to diverge. The root test is inconclusive again when your limit is 1, and you can look up examples of for each one as to why that is. So use the root test to determine whether the series converges. If the test is inconclusive, then say so. Okay, so you're going to want to use the root test when your terms are raised to a power, to the k power, right? Because then when you take the limit as k goes off to infinity of the kth root of the a sub n, a sub k, I'm sorry, and what that is then the limit as k goes off to infinity of your terms are k over 100 to the k, and then you're raising that to the 1 over k, because that's what the kth root is. And then here you'll multiply the exponents, and this becomes the limit as k goes off to infinity of k over 100, which is infinity. Means your the kth root of your terms just keeps getting bigger and bigger without bound, so then your terms must have been getting bigger and bigger without bound, right? And so therefore diverges. On this problem, didn't really need the root test. You can see by looking at your formula that k divided by 100 is getting bigger without bound, and then when you raise it to a power, that's getting bigger without bound. So then your terms are not going to 0, and if your terms are not going to 0, your series has to diverge. Okay, so let's move on. Again, we see that we're raising something to the kth power, so the root test it seems like a useful thing to do. And the problem tells you use the root test, but you're not always going to be told what to do, and so you need to start, how do I know what test to use? That's a very difficult thing. So for the root test, we're going to take the limit as k goes off to infinity of the kth root of the absolute value of the a sub k. Now notice here that these are going to be eventually positive because e to the negative k decreases and gets closer and closer to 0. So that's going to eventually be positive, so I'm not going to use the absolute values. Actually, starting at 1, it's positive. So those are always positive. Then this becomes the limit as k goes off to infinity of the kth root. It's easier to see it as 1 over k. And then you have 1 minus e to the negative k to the k. And then these will cancel out. And so then this will become the limit as k goes off to infinity of 1 minus e to the negative k. And so this you should know that this goes off to 0, and so then this limit is 1, and therefore your test is inconclusive. And you would have to find another test to use. But right here, that's all we're being asked to do. Use the root test to determine whether the series converges. If the test is inconclusive, then say so. So we're not being asked to show whether it converges or diverges, so we're free to move on. I didn't put these on your class notes because this is all in the book. I just wanted to run through all the tests in one time and talk about when we can use them. So the test is the nth term test, which is the divergence test. And so you just look at your series, and if the terms do not go to 0, then your series diverges, right? So conditions of convergence, there isn't one. This is the divergence test. If your terms do not go to 0, you're done. This test cannot be used to show that a series converges. That's the comment. All you can do is use this test to show that it diverges if the terms do not go to 0. If the terms go to 0, you have the harmonic series that diverges. So just because the terms go to 0 does that mean that the series converges. But if the terms don't go to 0, then the series diverges. Next test, it's not really a test. If you recognize that your series is geometric, the ratio of any term to any other term, the ratio of a term to the term before it is always the same number, then it's geometric. If your common ratio is between -1 and 1, then your series converges. And if your common ratio is bigger than 1, then your series diverges. This is again one of the few cases where we could actually then say what it converges to, and we have a formula for what it converges to. And so then it will converge to the first term all over 1 minus the common ratio. If you have a telescoping sequence, and it'll look like if a telescoping sequence when your terms look like this, b sub n minus b sub n plus 1, where the same formula is going to come up and eventually some terms will cancel out. When you have a telescoping sequence, you can find a formula for the nth term of the partial sum, and you could then take the limit. If the limit is finite, then your series converges, and it converges to that number. If the limit is infinite, then your series diverges. And so then, yeah, I don't think this is worthwhile to memorize. It's in your book, but we're not going to go over it. Um, Another special kind of series is a p-series. A p-series will look like 1 over n to the p. Another thing to remember is that if you don't have a p-series because of a 5 or a 10, that doesn't matter. A constant factor doesn't change anything, right? You can factor out the constant factor using the limit laws from the sequence of partial sums, and that is not going to change anything. So you can ignore the constant factors, numbers you're multiplying by. But if you have 1 over n to the p, if your p is bigger than 1, you're going to converge. If your p is between 0 and 1, you're going to diverge. And then we have the alternating series test, right? So if you have an alternating series, then you're going to have a factor of -1 to a power somewhere in there. It has to alternate positive, negative, positive, negative. And if your terms are decreasing and going to 0, then your series has to converge, right? Then you have the integral test, right? So you're going to use this one when you see a formula that's easy to integrate. If you see a formula with factorials, we don't know how to find the antiderivative of factorials, so you can't use the integral test. But if you see something, then you can use the integral test and basically exchange the series for the integral. And if the integral converges, then your series will converge. And if the integral diverges, then your series will diverge. The root test, you're going to use this when you're when your terms are being raised to a power, right? So if you see a power, then I'm sorry, if your terms are being raised to a variable power. If you see a variable power, you might want to consider using the root test. But it's also so if your limit is less than 1, it's going to converge, and if your limit is bigger than 1 or infinity, then it's going to diverge. But if it's equal to 1, it's going to be inconclusive. Ratio test, right? So we absolute value the terms, right? If we get a limit as n goes out to infinity of these ratios and get something that's less than 1, just like the geometric series, because that's what motivated this. If your limit is less than 1, then you converge. If your limit is bigger than 1 or infinity, then you diverge. And so also the test is inconclusive when n is equal to 1. Then you have the direct comparison test. So you should have the p-series and the geometric series memorized and know that they converge. If you can make an easy comparison and you have a series that can easily be compared to another series whose terms are bigger, then you can use the basic comparison test to tell you that your series is going to converge. If you have a series that's smaller, your b sub n is smaller than another series that you know that diverges, then you can use that to compare the two and say that your series has to diverge because your terms are smaller. Basically a challenging test to use, except in some special cases that make it really easy. If you're going to use a comparison test, the easier test is the limit comparison test, because then you compare the ratio of a sub n to b sub n, doesn't matter which one goes on top or which one goes on bottom, and if your limit is finite and not 0, then both converge or both diverge. And so that's basically the limit comparison test. Okay, so moving on to problem number 26. In exercises 17 through 38, use the ratio test to determine the convergence or divergence of the series. If the ratio test is inconclusive, determine the convergence or divergence of the series using other methods. Might want to pause and see if you can do this on your own. So we want to take, problem tells us to use the ratio test, so we want to take the limit as n, that's our counter here, goes off to infinity, of the absolute value of the a sub n plus 1 divided by the absolute value of a sub n. The absolute value is going to get rid of this factor, so we don't have that. And then a sub n means that we're going to put in n plus 1 everywhere we see an n. There's an n right there. We're going to put n plus 1 plus 2 is n plus 3. N plus 1 right there. And then n plus 1 plus 1, n plus 2. We multiply by the reciprocal of a sub n. So we have n times n plus 1 divided by n plus 2. Okay, so only one thing cancels out, the n plus 1s. And then in the numerator, we have a degree 2, or if we can rewrite this as the limit. No need to multiply it out. You can see that if you multiply it out, you will get a degree 2. The first term will be n squared. In the denominator, the degree will be 2 when you multiply this out, and the leading coefficient is, the leading term will be n squared. So this is going to have a limit of 1. If you want to multiply it out, you can. So let me just do that real quick. But when you have more complicated, there's really no need to multiply this out. You will get n squared plus 3n, and in the denominator, n plus 2 times n plus 2 is n squared plus 4n plus 4. Degree 2 over degree 2, so what you get is the leading coefficient of the numerator over the leading coefficient of the denominator, which is 1. And unfortunately then, this is inconclusive, and so we have to use something else, right? So again, if we multiply this out, then this becomes negative 1 to the n plus 1 times n plus 2 over n squared plus n. And if we ignore all but the factors, the terms that contribute the most growth, so this you should be thinking the series n over n squared, which is 1 over n. And so you just ignore the 2 and ignore the n, you'll get n over n squared, and you will have 1 over n. And so then you know that this series diverges, so then the absolute value of this series is going to diverge, right? But it's not asking about absolute convergence. It just says if the ratio test is inconclusive, determine the convergence or divergence of the series using another method. So it's nice to look at the absolute values, because obviously if it's absolutely convergent, then it's convergent. But if we ignore this part right here, then it's divergent, because we're going to compare it to this and it's going to diverge. But you can see that this is the terms are going to 0, because you have a degree 1 over a degree 2. It's alternating, and eventually it's going to be decreasing. So then this is going to converge by alternating series test. So same instructions. Use the ratio test. If the ratio test is inconclusive, determine the convergence or divergence using another method. Okay, so again, ratio test, we're going to take the limit as n goes off to infinity. When we substitute in for n plus 1, we will get 2n plus 2, because the whole thing gets multiplied by 2. So you get 2n plus 2 factorial. And then in the denominator, we get n plus 1 to the 5th power. That's the a sub n plus 1. And we multiply by n to the 5th power over 2n. factorial. Now again, you need to get comfortable with cleaning up these factorials. And you take the bigger factorial, that would be this one, and you break off factors until you get to this one. So 2n plus 2 factorial means that you start with your first factor being 2n plus 2. Then you take 1 away from that, and you get 2n plus 1. And then you take 1 away from that, and you get 2n. But that's what's over here. So then we stop there, 2n factorial. And then we still have this n to the 5th power. And on the bottom we have n plus 1 to the 5th power, and then we have the 2n factorial. The 2n factorials go away. Notice that what you have in the numerator is a degree 5 here times a degree 2 with this one, so then this is going to actually be a degree 7. I don't want to take the time to multiply all these out. And the degree of the top is 7, the degree of the bottom is 5. When the degree of the top is bigger than the degree of the bottom, your limit is infinity. It goes off to infinity. And so then, because the ratio is getting bigger and bigger without bound, that tells you then that your series diverges. Okay, now we start the tough part of, not being told what to do. We get to do whatever we like. We have to use any of the tests that we've gone over. It says use any method to determine whether the series converges, right? So this is kind of tough. And so the only way to get better at it is to practice it. Pause the video, try and decide what method to use, try and use it. And so again, if you ignore the 1, if you ignore this 1 right here, if you ignore this 1 right here, you'll have 1 over 2 to the k, which is just a half times 1 to the times 1 over k, and then that's a constant times the harmonic series. So you should get comfortable with the fact that this 1 isn't going to make it converge. This is kind of like the harmonic series, and so then this is going to diverge. The ratio test doesn't do well with these types of problems. The ratio test is good for if you have factorials or exponentials, but doesn't do well with these. So we're going to use the limit comparison test. Now, don't write this down. I'm going to erase it in just a moment. The 2k plus 1 is obviously bigger than the 2k. So when I flip it, 1 over 2k plus 1 is less than 1 over 2 to the k. Sorry, 1 over 2k. And this doesn't help because this diverges, and this, so then being less than something that diverges doesn't help. So the basic comparison test, it doesn't really apply here. It's not easy to use. So then what we're going to do is use the limit comparison test, right? Because we're going to compare this to the harmonic series, but it's not a basic comparison because the basic comparison doesn't work easily. We can make it work, but why struggle so hard? Let's just use the limit comparison test. So then here's what I expect you to say. I expect you to say that 1 over k diverges. You don't have to tell me why. You and I both know that this diverges because it's the harmonic series. And then we want to look at the limit as k goes off to infinity. This isn't the ratio test because you're not looking at the individual terms of this series. You're going to compare the ratio of a sub k to b sub k. From this series to this series. Doesn't matter which one's a sub k, doesn't matter which one's b sub k. So then this becomes the limit as k goes off to infinity of, and again, we just take the 1 over 2k plus 1 and we multiply by the reciprocal, which is k. And this limit will be 1/2, right? Because you'll have degree 1 over a degree 1, so you get the leading coefficient of the top or the leading coefficient of the bottom. And for a limit comparison test, as long as it is finite and bigger than 0, then they both do the same thing. Therefore, your series 1 over 2k plus 1 diverges. You could have also done this with the integral test, because this formula seems easy enough to integrate, and you could have done it that way if you like. That's up to you. Use any method to determine whether the series converges, right? So again, because of the factorial and the power, then this might seem like a good application of the ratio test, right? But if you rewrite this, you have k factorial times 10 over 3 to the k. And what you should see is that this goes off to infinity as k goes off to infinity. And this goes off to infinity as k goes off to infinity. So then by the convergence test, and the limit as k goes off to infinity of the a sub k does not equal 0, therefore diverges. You could do the ratio test, and it would take you a little longer, but by recognizing that you can write it like this, you can use the convergence test. If your terms do not go to 0, your series diverges. Use any method to determine whether the series converges, right? So again, ignoring this 1, you end up with k squared over k cubed, which is just 1 over k. And so then it's pretty certain that this is going to diverge. So then again, we'll use the limit comparison test. 1 over k diverges. And then the limit as k goes off to infinity of a sub k over b sub k will be the limit as k goes off to infinity of, and you can pause this anywhere along the way, try and fill it in, get comfortable with this. Doesn't matter which one you call a sub k, which one you call b sub k. A sub k for me will be k squared over k cubed plus 1 times k over 1. And you can see that when you multiply straight across, the degree of the numerator will be 3, the degree of the denominator will be 3. Same degree, you get the leading coefficient of the top over the leading coefficient of the bottom. And now here your limit is 1. Now we just got done with the ratio test, and if the limit was 1, that was inconclusive, but this isn't the ratio test. This is the limit comparison test, and as long as your limit is finite and not 0, they both do the same. So it's okay to get 1. Therefore, your original series diverges. So k factorial over k to the k. So again, with the factorials and the k to, and the exponents of k, this should be a good indication that we want to use the ratio test. So we're going to take the limit and you might think it's the ratio test, and if things don't work out with the ratio test, do something else. So the limit as k goes off to infinity of k factorial, a sub k plus 1 means you put in a k plus 1 everywhere you see a k, so you get k plus 1 factorial over k plus 1 to the k plus 1 times the reciprocal of a sub k, which would be k to the k, over k factorial. So this is going to equal the limit as k goes off to infinity of, and again, to clean up the factorials, you start with the bigger factorial. That's this one up here. That means k plus 1 times k, and since that's the same thing we have on the bottom, rather than writing k minus 1, k minus 2, we just write k factorial. And then over here we have times k factorial, k to the k. K factorials go away, and then over here we have k plus 1 to the k plus 1. And so then again, we have k plus 1, factors of k plus 1. The bases are the same, so we take one of these away. And over here we have k to the k. So we end up with the limit as k goes off to infinity of k to the k over k plus 1 to the k. Right, so the k plus 1 to the k, we took one factor away from this and we end up with a k. The factorials went away, and then the k to the k just came down. And so again, this is the limit as k goes off to infinity of k over okay. And so then okay, so once we get to here, we can again do the same thing we did last time. Take the limit as x. This time I'm remembering to change this to an x because we are going to use L'Hopital. And then we can write all of this as x over x plus 1 to the x. And then again, we're going to natural log it. And exponentiate it. To undo that, and that will allow me to take this variable and bring it down here. But again, in order to L'Hopital it, we need to bring it all the way down here. So this will be equal to the limit as x goes off to infinity, and we're going to exponentiate that, and then we will get the natural log of x over x plus 1 all divided by 1 over x. And now we'll L'Hopital it. And so now we'll L'Hopital it, and we'll take the derivative. And so then what we will get is e to the limit as x goes off to infinity. We can exchange our limit for the limit of the derivatives. Now the derivative of the natural log is 1 over x, and what 1 over x means is the reciprocal of x. So we end up getting x plus 1 over x. But then we multiply by the derivative of the inside, and so then the derivative of the inside is a quotient, so we have to use the quotient rule, which says to take the derivative of the top, 1, times the bottom left alone, x plus 1, minus take the derivative of the bottom, which is 1, times the top left alone, x, all over x plus 1 squared. And then in the denominator, we need to take the derivative of 1 over x, and the derivative of 1 over x is negative 1 times x to the negative 2. Okay, and so then this becomes e to the limit as x goes off to infinity of, now the x's will go away over here. Let me go ahead and give me a different colored pen. The x's will go away over here. And then one of the x plus 1's will go away. Right? And then you have in the numerator one over x plus 1 squared. I'm sorry, x squared plus x. And in the denominator, you have negative 1 over x squared. And so then this becomes e raised to the limit as x goes off to infinity of negative x squared over x squared plus x, which degree of the top is the same as the degree of the bottom, so this limit is negative 1, so you get e to the negative 1, which then becomes 1 over e, which is less than 1, therefore converges. Okay, there you go. Okay, so again, with the factorials and the exponentials, you're thinking ratio test. So you're going to take the limit as k goes off to infinity of the a sub k plus 1, k plus 1 factorial, divided by e to the, and when you put in k plus 1 for k, the exponent becomes k plus 1 squared, which is k squared plus 2k plus 1, times the reciprocal of a sub k, e to the k squared, over k factorial. Okay, so then this becomes the limit as k goes off to infinity of, and again, the k plus 1 factorial over the k factorial. Should be able to do that now. You can break off a factor of k plus 1. Here you'll subtract the exponents and you'll end up with e to the 2k plus 1. Now you have infinity over infinity, both the numerator and denominator go off to infinity, so you can use L'Hopital, but you should know that the exponential is going to grow a lot faster than the linear, and so this, you can use L'Hopital if you're not sure, but the linear grows faster than the exponential. I'm sorry, the exponential grows faster than the linear, so the denominator is going to get faster, bigger faster, and your limit will go to 0. If you're unsure of that, you can just use L'Hopital. So classify each series as absolutely convergent, conditionally convergent, or divergent. So when we look at the absolute value of the terms, we get the series 1 over k to the 4/3. Now 1 over k to the 4/3, that's a p series. Your p is 4/3. That's bigger than 1. So then p is bigger than 1, therefore converges. So that then means then that your series converges absolutely. Okay. So with the factorials, then we should be thinking ratio test. And so with the ratio test, when we take the absolute value, that -1 to the k plus 1 goes away. And so then the limit as k goes off to infinity of the a sub k plus 1 divided by the a sub k becomes just the limit as k goes off to infinity of 1 over k plus 1 factorial times k factorial, which cleans up to the limit as k goes off to infinity of 1 over k, which is 0. Therefore, converges absolutely. Likewise, in this problem, you have the exponential function. And so then this one here again should tell you to use the ratio test for absolute convergence. And so then we take the limit as k goes off to infinity the a sub k plus 1 is going to, the absolute value is going to get rid of this factor here, so we don't have to worry about that. But the a sub k plus 1, we're going to get 3 raised to the 2k plus 1. You're going to put in k plus 1 in for k and get 2k plus 2 minus 1, 2k plus 1. And then over here you will get k plus 1 squared, which is k squared, plus 2k plus 1, and then plus the 1, so you get plus 2. You're going to multiply that by the reciprocal, which is going to be k squared plus 1 over 3 to the 2k minus 1. So then this will become the limit as k goes off to infinity of, when you this exponent is bigger than this exponent, when you subtract them, 2k plus 1 minus 2k minus 1, and you're going to get the 2k will go away, and then the 1 minus the minus 1 will give you a 2. And then what's left is the k squared plus 1. There's nothing to cancel here with the k squared plus 1 and the k squared plus 2k plus 2. Nothing cancels out there. So that cancels out and we end up with just this. And so then the degree of the numerator is the same as the degree of the denominator. So what you get is the leading coefficient, the leading coefficient of the numerator, 9, over the leading coefficient of the denominator, 1. So your limit is 9, therefore diverges. All right, and so then the ratio test tells us that the series diverges, right? Because we got this 9, and so then it can't conditionally converge. It has to diverge. And so we're done. And so there's your homework, 17 through 73 odd. Have a good day.